Welcome back to our 42-day journey into mastering the standard template library in C++. We have already explored vectors in depth, and now we are going to meet their flexible cousin, the Deque. Today is day 8, and our focus is on understanding what a Deque is, how it functions under the hood, why and when we would choose it over vectors or lists, and of course, how to use it effectively in real code. By the end of this session, you will not only understand a TQ, but also be ready to solve real problems with me. A TQ or the double-ended queue is a highly versatile container that allows us to insert and delete elements efficiently at both the front and back. It's a sequence container just like a vector or a list, but with some key differences. Think of it as a hybrid. It gives us fast insertions at both ends like a list and random access like a vector. So if we ever need the benefits of both, the TQ is a perfect choice. We will explore exactly how and why next. Now let's peek under the hood. Unlike vectors, which rely on a contiguous block of memory, DQs use a segmented memory model. That means they allocate multiple smaller blocks dynamically rather than trying to grow one large contiguous chunk. This difference allows us to insert elements at the front without shifting the entire container, unlike with vectors. This structure makes DQs especially useful in scenarios where we constantly modify both ends of the sequence. Working with a DQ in C++ is straightforward. The interface is quite similar to that of a vector, with a few key additions. We can insert at the back using pushback and at the front using pushfront. Likewise, we can remove elements using popback or popfront. For accessing elements, we have front, back, add index, and the subscript operator. The queues also support clear, empty, and size, which make managing them quite convenient. Here's a basic example to show how we can use a DQ. First, we push a 10 to the back and a 20 to the front. So now our DQ contains 20 followed by 10. When we print the front and back, we get 20 and 10. Then we remove the front and back and we are left with an empty DQ. This illustrates how cleanly and symmetrically a DQ works from both ends. Now let's look at some practical use cases. One of the most common is solving sliding window path problems, where we need to insert and remove elements from both ends of a sequence. DQs also help in implementing undo and redo systems where actions are pushed and popped depending on user behavior. They are also great in palindrome checking, where we compare elements from both ends, and even in task scheduling, where we can dynamically add or remove tasks based on priority. In short, the queues show up in many real-world applications. So when should we use a DQ? The general rule is if we need fast insertions and deletions at both ends, and we also want random access to elements, then the DQ is the ideal container. If our problem involves a lot of insertions or deletions in the middle, a list might be better suited. DQs really shine when we work with problems where the ends are active but the middle stays mostly untouched. This table gives us a clear comparison of vectors, lists, and DQ. Vectors provide fast random access and are efficient for back insertions, but struggle with insertions at the front. Lists excel at front, back, and even middle insertions, but don't support random access. DQs sit right in the middle. They offer random access and are efficient at both ends, but not optimal for middle insertions. Also, unlike vectors, DQs don't store elements in contiguous memory blocks. Let's try a hands-on exercise. We will insert integers into a DQ using both push front and push back. After every insertion, we will print the front and back elements, and for a bonus challenge, let's remove all numbers greater than 100 from both ends of the DQ using a loop. This exercise helps reinforce our understanding of insertion, access, and conditional removal. To sum it up, DQs are highly flexible containers, giving us the best of both vectors and lists. They are efficient for front and back operations and allow us to access elements by index. They are ideal for real-world problems like undo systems, task scheduling, and sliding window algorithms. For homework, let's explore using Deque with iterators and try out STL algorithms like reverse, remove if, or rotate. Also take a moment to explore the official C++ documentation to deepen your understanding. Up next, we will explore the list container and how it differs in structure and usage. See you in day 9.